Alright, this is the last one on the 2019 exam. This is number 7. National average is 1.8. Means you've got to find a couple points here. It has a sig fig of a measurement deal here, so other than that, pretty straightforward in this guy. This says number 7. It gives us an equation. It says the student dissolves some oxalic acid into a flask. Then they're going to titrate the sample, which means at some point we're probably doing MV equals MV. It has dark purple color. Gives us a balanced equation. It says identify the species that was reduced in the reaction and justify your answer in terms of oxidation numbers. So when we look up here, check the weird things first. Leave hydrogen and oxygen alone. Check the other stuff first. This manganese in MnO4 -1 is a +7 oxidation number. And it's going to Mn with a +2 oxidation number. So identify the species that was reduced. So that permanganate, I would put MnO4 -1 is reduced. And then it says justified in terms of oxidation numbers. The manganese oxidation numbers go from +7 to +2. And what we had there with the +7 and +2 is probably good enough, but why not say it? So that's part A. You get a point for it. Part B is a lot of reading there in the question. The student uses 50 ml burette, adds the KMnO4 to the oxalic acid until faint lavender color is observed. That's the end point in that titration. The initial and final volume readings are given to us in the burette. Write down the initial and final reading and use them to determine the volume of the KMnO4 that was added. I'm gonna do this in the right order here. I'm gonna do volume final first, because final volume minus initial volume will give us volume used, right? And so I'm gonna write the numbers in that order: final, initial, total. So my final volume here, and you have to look at your paper. And I think I said this in the last video where we had to measure something like this. If they're in between two lines, I'm calling that a half. If it's right on the line, I'm calling it a 0, right? So that guess digit, guess a 0.5 or guess a 0.0. Don't get all fancy and say, well, that's a 0.68 or something, right? And so when we look here, this is between 29 and 30. Don't call it 30 point something, it's embarrassing. It's 29.5 something. And so my final volume, I'm putting at 29.55 milliliters. It wanted the final and initial volumes. Make sure you write them down. This thing is accurate to the tens place, which means we have to go hundreds place when we write this thing out. The initial in between 3 and 4 is 3.123 and a half. So I'm going 3.3, and then I'm going to guess that guy is a 5 as well. So 3.35. So there are my final initial readings. And so there's my final minus my initial, and that equals the volume that I used. That's all part B wanted. 26.20 milliliters is my volume used. You get a point for doing subtraction. Key to victory there is sig figs, the right number of sig figs. These are both to the hundreds place. When you're subtracting, it's least accurate place value, which means that guy has to be the hundreds place. If you put 26.2 there, you get nothing. You get no point for it. Does that mean? I don't know. I don't think so. If you're planning on doing real research, then you need to go to the appropriate number of sig figs to make your research valid. And so it's sig figs. Nobody likes them, but you should be good at them at this point. Given that the concentration of permanganate that was added was 0.0235, calculate the number of moles of permanganate. Don't get confused because the potassium is there, right? The potassium is a spectator ion, so we're ignoring it. They gave us the molarity of the permanganate. We have the volume of the permanganate, and so If we do the 0.0235 that they gave us, 0.0235 molar, and it's not, you can write molarity times volume equals moles, that's fine. There's our generic equation. Molarity times the volume has to be in liters here. That's 0.02620 liters. And that will give us our number of moles, and it should be small. And I got 6.11 times 10 to the negative fourth moles of MnO4. That was added. Good? That's part C. Then part D, last question on the whole 2019 exam, says a student proposes to perform another titration using the same amount of oxalic acid, but this time they're going to use 0.00143 molar potassium permanganate in the burette. Would this titrant concentration be a reasonable choice if the student followed the same procedure and used the same equipment? And the answer is no. And here's why. When we used 0.0235, it took us 26 mils, half the volume of the burette. If we were to cut the concentration down, in this case, we cut it not, what do we have, 0.02, we cut it not in half, but down, I don't know, 20 times, right? And if we cut the concentration down 20 times, what has to happen to the amount of volume we need? It has to go up 20 times. And so we would need 400 milliliters of that solution in order for this, in order to find the equivalence point. The problem is our burette only holds 50 mils of solution. So no, the small concentration would cause us to need more volume of solution than our burette could hold. That's your answer. 1R, 1T on burette. So no, the small concentration will cause us to need too much volume, more volume of the solution than our burette could hold. You might even put to reach the equivalence point. That's our fourth point. So point for the oxidation numbers, point for the volume of the right number of sig figs, point for multiplying molarity times that volume, and then know why too small a concentration. That's it. That's 2019. Have a good day.